Greetings again, this is Timur. It's 7:33 right now in Pacific time, and we're ready to start. Welcome to the webinar about migrating to exabyte.io and digital collaboration. Before we start, a couple of notes that you should know about. The goal of this seminar is to help users understand what exabyte.io is and how to benefit from using it. This is the second series of our monthly webinar progression. We speak about advanced topics on third Friday of the month, and it's today. Every participant should be a registered user of the platform. Everybody will receive this presentation in a PDF format with links to the specific subjects explained in documentation. If you have questions at any point in time, please use the chat functionality or Q&A to ask those questions. We'll have specific time slots to answer them. And at the end, we can just have a quick discussion. We'll assume that the webinar attendee is an experienced computational material scientist, familiar with tools like Quantum Espresso, VASP, or similar. And we will assume that the user understands the basics of Linux and Unix interfaces and has an established set of scripts or input files to perform calculations using the computational material science engine. So we'll speak about migrating these scripts and input files to the exabyte.io approach and how to work collaboratively with other scientists after this migration. For the migration, there are really two options. Users can either bypass the web interface and use alternative connection options to access command line environment and use existing scripts, input files to run simulations. This is a quick way to start for anyone who is familiar with command line, but command line usage is error prone and it's difficult to reuse every single time. We have to create a new document, a new file, a new script, and there is no validation in it, and it's difficult to share information on the command line. The second option would be to adopt the exabyte.io approach and create material entities in the platform, create workflows in the platform, and create jobs with the material and workflow information. This will require learning our approach, and it does have some learning curve with it, but it makes this approach reusable for multiple materials and easy to review and share. The collaboration options essentially also stem from the two options that we just discussed. Users can either bypass the web interface and use alternative connection options to collaborate through the shared file system, or they can adopt the exabyte platform approach, where we have a way to collaborate on the entities with role-based permissions within one or multiple organizational accounts. Okay, and I will explain both of this today. Here is a brief agenda. We'll speak first about the platform infrastructure, alternative connection methods, what is under the hood, what's the file system looks like. Then we will speak about materials and migrating the structural information from PWSCF input file to the platform. Then how we can migrate the workflow logic that usually is bundled together inside one input file for PWSCF, which is part of Quantum Espresso. And then we'll speak about how to run simulations with the entities created in parts 2 and 3. And then we'll proceed with discussing the collaboration. Okay. Some of this functionality might require having a command line access, and the webinar attendees can request this access. We'll add them to the webinar account where they can try how to use this functionality. Okay. All right, let's start with the platform infrastructure. Here is how it looks like. I know it appears complicated, but there are parts here that we need to know about. First of all, there is the common way to connect to the platform is by using the web browser. And here is the example. The user opens the web browser on their computer, connects to the web interface. However, there are three alternative connection methods actually through remote desktop and web terminal, SSH, and through RESTful API. So we have 4 total connection methods that could bypass the web interface. And we will speak about 3 of them today: the secure shell connection, remote desktop, and web terminal. The secure shell connection is based on a key pair and requires any SSH client. The web-based command line terminal is equivalent to SSH for all purposes, but it can be started from the web browser without any client required. The remote desktop connection can also be started through a web browser and can help users run visualization applications such as Vesta, Expression, or something similar. And there is also an option to use the RESTful API, which provides programmatic means of communicating with the platform entities. This is more interesting for people who develop web applications, for example. So there could be a web application that uses Exabyte platform's RESTful API to get the entity's information to run the jobs and do things like that. We will not cover it today, but if you have questions about it, we can dig into that deeper. To access the SSH connection, one needs to upload the public key into the platform and keep the private key on their system. This will establish the connection, and by using any of the terminal clients, you will be able to connect to our infrastructure. The same can be done from the web by, the same can be done from the web by using the web terminal option. So if you open the sidebar, here is the terminal that allows for the command line connection to get started. There is a certain way to do copy paste within the terminal, which can be started by clicking Ctrl, Shift, and Command. And then there is also a way to upload and download files by dragging and dropping it onto the browser window. The remote desktop can be opened next to the web terminal. There's a remote desktop option, which essentially starts a graphical user interface, a Linux session, and there are a set of applications that users can run within that session to analyze the data to get access to the platform infrastructure. To understand which infrastructure we have access to, we have to speak about the file system. And here is how the file system is structured. Users connect to the login node, which has access to multiple computational clusters that are hosted on different cloud providers. So cluster 001, for example, could be hosted on Amazon Web Services, which it is today in the production system. Cluster 002 can be hosted on Microsoft Azure, for example, or we also support Google Cloud and Oracle. And that is a way for us to have different kinds of infrastructure within a single cloud provider. There could also be different kinds of infrastructure, different types of hardware. And enterprise users can also request a specific cluster to be associated only with their enterprise. So this is a flexible way to get access to multiple different computational systems. And when we connect through any of the alternative connection methods, we connect to the login node, but we have access to all the files residing on subsequent clusters. To do that, we need to navigate into the links that are present inside the home folder on the login node. So if you navigate into cluster-001, we will be able to see its file system. So we automatically get linked to the home folder for the user on that cluster node. Within that home folder, we also have a set of specific directories, such as the Dropbox directory, a directory called beta, and job script templates, which contains the templates for the command line job execution. And here is the directory for the organizational account that I am associated with. So I am a member of exabyte-io account, and that's why I'm seeing a link to its folder, shared folder, on the command line between all the account users. So the Dropbox folder, as we call it, is very similar in concept to the Dropbox service, it has a hot cache, a small amount of data that is available everywhere on the platform. It is available on the web interface, on the computational master when the execution of the computations is performed. It's available on the compute nodes when a large-scale job is running, and it is available on the logging node as well. So we can put data into it from anywhere, and we can access it during the calculation time. It's not meant to store bulky data. It's meant to store things like scripts, certain potentials, small data that is hot and necessary to access during the calculation time. Jupyter Lab is also started on this folder. So when users have Jupyter sessions, they can share the IPython notebook files through this folder as well. Then there is the data folder that contains the jobs that originate on the web interface. The jobs are organized into projects, and every single job has a certain naming convention on the command line. For example, if we have a job that is part of the project default for a user named Steven, the job will reside under Steven-default subdirectory inside the data folder. And its name will reflect on its actual name, its human-readable name inside the web application, with an ID inside the database attached to it. So it will look something like this, with the slugified, as we call it, machine-friendly human-readable name, plus the ID. So that is the way for you to understand which job corresponds to which folder on the infrastructure side. For organizational accounts, we have a similar convention, but it is not, the jobs are not stored inside the home folder for the user because there are multiple users within the same organization. It's instead hosted under the share groups account name folder in a similar manner. Now, why it's important to understand this? It's important to understand this because there is a certain set of functionality that we do not yet support today on the web application, for example, but we do support it through remote desktop. So there is no way to visualize the charge density on the web application yet, but we can visualize the charge density using XCrystal. And here is an example. I apologize, this is Fermi surface, but we can also visualize the charge density using tools like XCrystal as well. So if we pass the right location produced during the calculation of the file produced during the calculation to this program, we will be able to utilize this additional functionality. Okay, so here is a brief summary for this section. Remote connection is an alternative way to access the exabyte platform. It can be enabled upon request for certain kinds of service levels. There are three options: web terminal, remote desktop. Both are inside the web browser, and an SSH session. Remote sessions are connected to a login node with a separate home folder for each user. Home folder has links to directories for compute clusters. And command line jobs must be submitted from within a cluster directory, not any other ones inside login home. Because when we execute the jobs, we have to put them into one of the infrastructure domains, so into one of the clusters. And if they're started not under the cluster subdirectory, we have no idea which one to put it into. There is a variety of software packages available both through remote desktop and through command line modules. It doesn't look that we have any questions as of yet, so I'm going to proceed and speak about materials right now. And specifically, I'd like to demonstrate how we can migrate the information about the materials, the structural information about materials, from an input file of Quantum Espresso to the exabyte platform entity. Here I have an example workflow for a Quantum Espresso calculation with a self-consistent field and then a non-self-consistent field parts. Right? So we have input files that contain the structural information about the workflow, some information about the precision that we use. So what we will do now is we will create a material inside the platform using this information. The first step would be to understand which material we're dealing with here. And for that, we have to review the input file. We see now there's certain structural information. There is no crystal lattice assumed. Abrev is equal to 0. There is a cell dimension parameter that we need to know about, which is given in bores for Quantum Espresso. And there is a cell parameters section, which has the crystal lattice parameters. And there are atomic positions in crystal coordinates. This concludes the structural section. So then we go to the infrastructure, to the platform, to Exabyte platform on the web, and click on the plus button to open Materials Designer. When it first opens, it has the default material for this account, which is Silicon FCC in my case. It is convenient to clone this information, not to work with the original Silicon FCC material. We clone it, create a hot copy, so a copy that doesn't exist in a database, it only exists in this current online session. And then we rename it, preparing this as a template, as a stem cell of a sort to be edited now. All right. The next step is when we transfer the crystal lattice information from the input file to the platform. So we set up triclinic as the lattice type because we didn't assume any lattice type in this input file. And then what we do is we transfer the lattice parameters. So there is a certain z-axis parameter that is used in this file. And we need to copy that and copy the lattice parameter itself. We then convert pores to angstroms, get the information in angstroms, and put it into the lattice. Right, so all A and B are equal to that in the lattice, and then we multiply the C parameter by the factor that we extract from the input file. Okay, and as the input file has it, all the angles are 90 degrees. So here's how we transfer the crystal lattice information to this new prototypical material. As a next step, we transfer the crystal basis information, and that is easy because we already have it in crystal coordinates inside the input file. So we just copy and paste it. And here we go. We have the information about this material transferred into the platform in full. And the next step is when we save this information as a new material inside the platform. We can tag it, and I'm adding tag from PWSCF here so we can quickly find it in the list of materials in the future. Click OK, wait for this operation to finish. Operation is successful. We exit the Materials Designer session, and we see that we now have a new material with the correct tag inside the materials list. Okay, so that's how we transfer the information from a Quantum Espresso input file to the Exabyte platform entity. Another option would be to use a converter. So we do not support direct import of the PWSCF input today, but we support direct input of POSCAR and CIF files. So what we can do is we can use this online converter to convert the Quantum Espresso file to POSCAR, and then upload POSCAR directly into the platform. And I covered that step in the seminar from 2 weeks ago. Now, the input files for Quantum Espresso also contain the workflow logic. So first we execute the SCF in, and then we execute the NSCF input file. So to transfer this workflow logic, we'll have to construct a workflow from scratch. And I will explain now how to do that. So our first step is to, again, inspect the input file, understand what are the parameters used inside this workflow, what is the logic, the execution progression. And then we go to the list of workflows and click on the plus button to open the Workflow Designer session. And just like a Material Designer session, it opens with a new workflow, which in this case is empty. So there is there's one subworkflow, but there's no meaningful information inside it. So what we have to do as a first step, we'll edit the name to be able to find this workflow in the future. Call it new workflow from PWSCF input for now. And we'll edit the name of the first subworkflow, SCF and SCF subworkflow. All right. The second step is to add a unit to this first subworkflow. For that, we scroll down. Users can also modify the applications, modify the versions that are used in particular builds. For this example, I just keep everything as default and navigate to the units flowchart and click on plus button to add a unit. Here we have a single workflow that contains one subworkflow, and now it contains a single unit. A subworkflow contains a single unit. Again, we assume a certain default parameter, pw_scf, which actually fits our needs in this case. If we open this PWSCF unit, we can see that there are other flavors available, like NSCF, that will be handy in a couple of minutes. And it has certain properties associated with it. Excuse me, let's come back here. This unit has certain properties associated with it. There's certain monitors and the input text itself. So here, what we need to do is we need to understand how this input text is different from the one that we are dealing with in the original input files, and migrate the missing keywords. So for example, we don't have the lk_point_ directory there, and we'll move this information and paste it into the control name list of the input file. Okay, and we have to do that for all the other name lists that are relevant, like system. I'm adding the smearing parameter there, and for the electrons field, I'm adding a particular convergence threshold and removing the original text. Okay, so we see that there are no ions or cell fields there, so we can remove those name lists. And the material information itself, we don't have to touch because it will be populated automatically based on the material that we pass to this workflow. Now we can preview this file, the template file, and we can see that it is properly created based on the material information. All right, so now we have migrated the first input file into the first unit of a subworkflow inside this workflow. Now the time is to add the second unit. For that, we repeat the process, click on the plus button and click apply. The second unit has the NSCF flavor. So the calculation type here is NSCF, and there is a certain, again, set of default keywords that we pre-populate for the NSCF flavor. We need to see how it's different from the original input file and migrate this information. Okay, so we repeat all the same steps. For example, there are tetrahedral occupations that we want to use, and do that here. All right, clean up this file again and preview it just to make sure that we have the correct final textual output. So this is how we translate the information from the input files into the workflow. And the last step is to save this newly created workflow. I rename it SCF and SCF workflow from PWSCF input, and add a tag from PWSCF to be able to find this workflow easier in the list in the future. Excuse me. And the last point here is to click on the save button, which looks like a check mark, and navigate to the list of workflows where we can see this newly created one at the top of the list. All right. So here is how we create a new workflow from the two quantum espresso input files. Another option, option number 2, would be to copy a similar workflow from the workflows bank and adjust its parameters. So in the first option, we have started from scratch from a workflow that contains nothing inside itself. But as we have many more users joining and creating content on our platform, it's likely that some of them have previously run or attempted to run or created already the workflows that you are going to be dealing with on a regular basis. So what we can do instead, we can copy that workflow and modify it according to our need. So we would navigate to the workflows bank by opening the left-hand sidebar and clicking on bank and workflows and searching for the desired workflow. So if I want to run the band structure calculation, I'm typing band structure inside the search bar at the top and selecting the band structure and density of state workflow from the list. Here's a quick tip. Instead of selecting the first one, we advise novice users to select the ones that are owned by the curators account. So there is a special account we call curators that consists of users that are affiliated with the Exabyte platform. So we have curated the workflows, the bank workflows that are produced by that account and make sure that they work well. So it's usually a good starting point that can be further modified by users. Okay, so now when we click on copy and the notification pops up, we can see that there is a copy of this bank workflow inside our accounts, our users workflow collection. All right, do we have any questions at this point? Yes, there is a question about where can I get the presentation file so I can study the system comprehensively while doing hands-on. Yeah, this is a good point. We have always assumed that we will be sending the presentation files after the presentation itself in a follow-up email. But this is a good point. So in the future, I will include the prior presentation files so that you can follow these presentation as I speak. This is a good point from Bernardo's. Yeah, we'll do that in the future. So now let's proceed to discuss the jobs. And here, again, we have two options to produce the simulations using the information that we have at hand. The first option is to upload the input files on the command line, to upload them to the infrastructure and use the familiar command line syntax, resource management system, batch scripts, and execute calculations through command line. I have covered this option in the prior webinars about months ago and before that, so I will not speak about it in details today. You can watch the recordings. Instead, I will speak about the second option, where we are reusing the entities that we have created from the original input files. So we'll reuse the material and workflow that we have just created to set up and run a job. So I have created this calcium, tungsten, oxygen 4 material, and I will use that plus the workflow, SCF and SCF workflow from PWSCF input to now create the calculation. First step in creating a job is to navigate to its project. The project is simply a collection of jobs that are associated with a specific task. For example, if you're dealing with a particular publication, we need to prepare a publication. It's convenient to organize all the work for this publication inside the project. And by default, every account has two projects, a default project and an external project. We suggest that you start with the default project. The external project is there to contain the information about uploading external data that is not generated on the Exabyte platform. So if you upload vast calculations, for example, that you did elsewhere, they will appear inside the external project as jobs. So let's go to the default project and click on the plus button to create a job. Now we have the materials interface and workflows and compute tabs. And then at the top, here is the header where we can modify the job name, for example. This is where I start again. I modify the job name to reflect on the material that is used inside it. And then I proceed to select the material for this job, which is already present inside my account. So I'm selecting this newly uploaded material, newly created one. Then I'm doing the same for the workflow. Selecting the workflow and clicking on select items. And the last part here is to adjust the workflow parameters. So the workflow logic itself is not modifiable during the job creation. We did it on purpose so that the workflow data is consistent. So we cannot add another unit to it or change the logic inside the workflow. But we can adjust parameters such as those that are specific for the precision of this workflow. There's a set of potentials, for example, that we use by default, and users can adjust those inside the workflow. And it can be viewed by opening the potentials panel. And there is a set of specific options inside the units that can be modified. Right, so if you click on the preview tab, we can edit the preview tab directly when necessary. So here I'm going to compare the original keypoint grids from the files that I've been using as the source with the keypoint grid inside the template. And I'm seeing that they're not the same. We have a certain convention, again, that we applied by default for this input file. And in this case, it's different from what was in the original input. So what I have to do is to navigate into the important settings panel and adjust the key grid parameters inside the form. So I'm putting it as 4x4x2 according to the original input. And for NSCF, I'm putting it to 8x8x6. All right. So now I'm sure that the output actually reflects the correct values for this precision parameters. And I'm adding a note about that to the job name. Next step is to set up the compute parameters, which is a task of its own. There are things like the time limit for which this job will run, the type of cluster that we send this job into. And for this relatively large calculation, this is a relatively large cell for our material, we always recommend starting with the ordinary regular queues, which are meant for most production tasks. And I'm using 18 cores, which is the recommended size for cluster 001. And I'm also ticking the box to receive notifications about all updates for this job. Okay, the next step is to click on Save the job button. And here we have it inside the list. When the job is first created, its status is P, which means pre-submission. So it's ready to be submitted. It is created, that there's an entity in a database, but we have to actually submit it for execution, which is what I'm going to do next. So I'm selecting the job in the list, submitting it for execution, clicking run. It transitions to the submitted status, and shortly after that, there is a notification that says that within 10 minutes, the job will be started. We'll have to provision the cloud infrastructure for it, and it usually takes a couple of minutes to do that inside the OR queue. As you can see inside the G queue, it could be immediate because the D is meant for debug calculation, so we keep extra infrastructure running there at all times. So within 2 minutes, we have the infrastructure provisioned and the calculation starts. It goes into the active state. And now we can open the job entry, if we click on its name, and see what is happening inside the workflow. Now, the active subworkflow and the active unit is highlighted in orange. So we can click on the unit again, and we can see the unit output in the real time as it's been produced on the infrastructure. And we can monitor the convergence parameters too. So this is the convergence for the electronic structural calculation. Right? Now we can come back to the list of units. When the first one is finished, it's turned green. And we can see how the second one is progressing. This is a production type calculation, so it will take some time for it to finish. You can see after a couple of minutes, the calculation is done. And both of these units are turned green. The next step is to view the results. We started with just 3 tabs when we created the job: materials, workflow, and compute. Now we have 2 additional tabs added here: results and files, during the job calculation while it's active, and when it's finished. We can see results and files. So if you navigate to the results tab, we can see the properties that were extracted during this calculation per each unit. So PWSCF has a set of properties associated with it, and PWNSCF has another set of properties as well. And if we go back up and click on the files, we see the list of all files produced during this calculation, and we can download and preview some of these files from the web. Okay. There is also a way to see the cost associated with this job by coming back to the compute tab and clicking here on the cost preview. Now, after we are done with this calculation, and that's the whole purpose that's the whole reason why the web-based approach works better, is what we can do there is we can share this calculation between multiple accounts. So I have performed this calculation under the webinar account, but now I'd like to see it when I log in as under my personal account as Timur. So what I will do here, I will share, click on share, select this entry in the list. I click on share and select my personal account there to share this entity with. Click on read to give myself read permission there. And now we can see that this entity can be read by myself and by the public. So the public is an account that is associated with all users, which means that this entity is visible to all the platform users. So now I'm sharing this entity with myself directly to see it under my account. If I change the session, if I change into my account, which I'll explain how to do in a minute, I am able to access this entity there as well. Okay, so here's a quick summary about the command line versus user interface jobs execution. The command line approach is quick to start with, and it's familiar to many already, but it's difficult to modify the input files every single time, and it's error prone. Unless we're using some programmatic tools, and even when we are using those, there are multiple times that computational scientists have to face all sorts of problems when we forget something, for example. And it's also difficult to store the data only on disk for the purpose of collaboration. For the UI jobs, we have to invest some time to understand how to deal with them. But once we have created the workflow, it can be applied to multiple materials at once. Yeah, the data is automatically organized in a database. So if we need to run some analytics in the future, which is the common approach today is to have data aggregated in the database and then do some sort of data analytics or machine learning on it. We won't be able to do that on the command line. In the user interface, if we run jobs from the user interface, we will be able to do exactly that. And then collaborating within the user interface is much easier as well. Most of the people deal with a limited number of workflows, usually 5, 10 at most. So when the required workflows are migrated, there needs to be modified very little. We mostly iterate through multiple different material formulations in our work, and materials are easier to adjust. Okay, So now I'm coming to the final part of this presentation, speaking about the sharing and collaboration. I have started on it a bit, but let's first talk about what kind of accounts are available to the users. Everybody has a personal account associated with a particular person. So we would like to make sure that when you log in into a platform, we know who you are, and everybody has their personal account associated with them as humans, right? And then for myself, here in this example, I have access to multiple other organizational accounts, or team accounts, or shared accounts. So here I have a seminar account that I have been showing examples for, and exabyte.io account that we do in production work in. And here I can demonstrate how to change from one account to another. So I'm opening the right-hand sidebar, clicking on my accounts to access this view, and then clicking on seminar name there to start using the platform under the seminar account. And what happens then, the interface automatically changes to reflect the entities that are produced under that account that I have access to. So the projects are now not my personal projects, but the projects of the seminar account. The materials and jobs and the rest of it will also reflect on the data produced within that account. When I'm done, I can come back to the list and navigate back to my account, so you can see a different set of projects and other entities. Okay, so this is how we can navigate between multiple accounts. For the organizational accounts, we have a comprehensive permission-based, role-based permission scheme. So here we can create, first we can add people to this account. Now I only have demo, for example, as the member of this account. And now I'm adding another user, a few of them actually. So now I can see that besides the original user, there are 3 additional users that will be able to access this account. How exactly they will be able to access this account is defined by the teams. So through teams, we can have a role-based permission scheme. When we create a team, we assign a certain set of permissions to it. It usually helps to add a quick description to it as well and a name. But the most important part is the permission scheme. So now we have read, edit, comment, and execute. Read and edit are already implemented. Comment and execute are there as placeholders for now, for future implementation. But the two, read and edit, provide different kinds of permissions. So for read, I will only be able to see the entities, and for edit permissions, I will be able to actually modify them when I see them. So I'm adding the read permissions there, and now this test team will be able to grant the read permissions to all its members. Now let's see how we can add members to the team. We navigate to the Teams tab inside the account. Click on the team name, click on the plus, and now we can add users to this team. Okay, so now these 3 users will have the read permissions on the entities that are associated with this team. Now let's see how we can add the entities to this team. And that can be added in exactly the same manner. So I come back to the team page. We have projects, materials, workflows, and jobs that are associated with this team. And I can add materials to it by clicking on the plus button and selecting the materials from the list. So this way, the organizational account administrators can delegate a certain set of permissions per each item, per each entity, to a certain subset of users within the account. So it's a very flexible, perhaps a little burdensome in the beginning, but a flexible scheme that can delegate permissions to account members. Now, there are also certain access levels enabled for the entity. And these access levels can be within a single account, which is there by default. It can be, the entity can be shared with another account. the entity can be shared with all other accounts in the platform. And it can also be shared externally outside the platform. So sometimes you collaborate with people that are not yet our platform users, and they can still access the information on Exabyte platform by having this type of access level enabled. And then we also have a specific type where we can share the entity on the web with anybody, and it can be indexed by search engines. So you can find it on Google, for example, which is useful for publications and for demonstrating the work to other people. So I will now show you how to assign these access levels to the entities. So I'm selecting the first one, which will be shared with a specific account in the platform, selecting that account, clicking on the read. And as we can see, now the shared tick box check mark is there. So this entity that belongs to my personal account is now also shared with the webinar account. I repeat the same for the second entity and now select anyone, now select public, so all platform users. And this makes the entity public. I will explain exactly how the public can see this entity in a moment. If I want to share this entity with anyone that has a link to it, I select anyone with a link. And similarly, I also select anyone on the web for the fourth entry. Okay, so now we have these different access levels for these different entities. To be able to see the entities that are shared with my account or shared publicly, we have two shortcuts in the left-hand sidebar called shared with me and shared publicly. So essentially, the items that are shared with specific accounts are called shared, and the items that are shared publicly, so with all other accounts, have this public check mark for them. So let me show you how we can see the items that are shared with me. Or if we navigate to the shared with me tab, we can see all the materials, properties, workflows, and jobs that have been shared with this specific account. So once I navigate and start using the platform under the webinar account, I can see the shared with another account job that I have just worked with in the previous example. And we can see that Timur is its original creator. Okay. So here we have a material. Here's how we can share it with another person or with another account. Just like in the previous example, following exactly the same procedure. Now, the accounts that are shared publicly, so this is the example where we share the entities in a private setting, right? The accounts that are shared publicly can be accessed by navigating to the left-hand sidebar, shared publicly. And here we can see the work that comes from all the platform users. Unless they have the private data enabled, which is usually the case for and any kind of enterprise usage or paid subscriptions that we specifically establish. This data is accessible for everybody to collaborate, to view, to interact with each other. So if you go to the left-hand sidebar and click on Share Publicly, we can see materials, projects, and jobs for all the users that have this information in the public domain. And we can see the activity in real time that happens in the platform. Okay, so now I can open the Shared Publicly, navigate to the list of jobs, scroll down to the bottom of it, change maybe the number of items shown on the page to 50 to scroll through the job sets at the top. And here is how we can see the latest work happening inside the platform. Now, when we collaborate with someone, it's convenient to add a quick description to the entities that we work with so that somebody else can see this description, and this is how we can communicate between multiple people. To do that, we have enabled this information or description for the item. So when you navigate to a job, for example, you can click on this icon in the header, and you can adjust this description, and we support Markdown language inside this text field. So you can put links and things like code, for example, source code, into this description. And here is how it looks in the platform when we enable the column for the ID and description. This is a quick way to remember what happened inside the calculation. You can apply that for materials and workflows as well. So this is a human-friendly way to mark the entities and describe them. Okay. And now for the last couple of minutes, I wanted to mention that the other way we can collaborate and share entities information is through the entity bank. I have described this briefly during the webinar 2 weeks ago, the Getting Started webinar. But essentially what the entity bank is, it's a collection of unique items, unique entities within the platform. So for each account, they have a subset of materials that they work with, which is unique for this account. But it's not unique inside the platform. So every account has Silicon SCC as a default material created for each account when the users first log in. But all these default materials, they correspond to a single entry inside the bank collection. The entities are by default accessible by other accounts unless there is a private data enabled for this account. So when the account has private data enabled for it, the bank entities, they are also private for this account only. So no other accounts can have access to it. This is a flexible scheme. Again, this is another layer of complexity and another layer of flexibility that users can rely on to share the information about materials and simulation workflows. And that's why when users create new workflows, other users can see the workflows that they have created and reuse them in their daily work. All right, so let me summarize here. The entities can be shared within one account for a secure and safe collaboration with a flexible set of permissions implemented through account teams and specific types of account members like administrators and account owners. Sharing between individual accounts is also possible. Sharing with all platform users is possible, and with external non-registered parties is also implemented. We have entities that support metadata, such as description or tags, to help users exchange information about these shared entities. And we have unique entities consolidated inside the entity bank collections. So all these 5 points should provide a comprehensive ecosystem, a comprehensive way to collaborate and share information between the platform users and even external parties. All right, I think I'm done with the explanation here. Let's see if we have any questions at this point. No questions in the chat, nothing in the Q&A.